So good evening everyone. So we are happy to have Professor Rajaram Lakkaraju from IIT Kharagpur. He has graduated with a bachelor's degree in mechanical engineering from Acharya Nagarjuna University. After which he did an MS at JNCSR, Bangalore, and then a PhD with dental occlusion and nuclear prosperity from the University of Twente. With a brief stint at BITS, Goa, he has joined IIT Kharagpur as a faculty member in 2015, where he is currently working. So, Raja, today we'll be talking about particle-laden turbulent fluids. So, Raja.
Hello everyone, am I audible? Okay, great. Thank you very much. First of all, my sincere thanks to Kanna, Mani and GFL team members, and also my sincere thanks to Aerospace Department for giving me a chance to present whatever the small things I know about particles in turbulence. And it's a wonderful experience being at IIT Madras. And my name is Raja. I work at IIT Kharagpur at the Department of Mechanical Engineering. And we have a small group which we call turbulent interfaces and dispersion. And Abhishek, right now what I am presenting is his PhD, this is work. Recently he has graduated with PhD. He tried to work on turbulent channels suspended with particles. These turbulence typically shear stress based or friction based Reynolds number around 400. In that, something like 1% of particles by volume, if they are present, what kind of properties they will show, and especially do they reduce, modulate the turbulence, or perhaps enhance the turbulence? What happens to local drag? These are the questions what we try to ask. And especially on wall friction, turbulent characteristics. And is that happening in the bulk zones or something near the walls, basically where log and subviscous layers are there? Do they get modulated? And that's the question what we are trying to ask. So in this talk, basically log layers, structures, what it means, turbulent structures, something about kinetic energy budget, what are the future challenges for this work, I will present. Our group, basically a small one which mainly works on turbulent multi-phase flows, industry-relevant problems like boiling, condensation kind of issues, maybe sprays. The second one is environmental related kind of multi-phase flows, especially sea spray ejections we are trying to understand. And basically I'm trying as a computational guy, so accelerated CFD using machine learning we try to work on. Basically, the toy models, what we try to look at, something like heated jets via direct numerical simulations. What happens to these structures if one is locally heating them? Maybe something like methane gas sequestration issues. So bubbles are rising inside big columns. How do they really diffuse? What kind of clusters happens? How do they really break up? This kind of issues. Something about particle trapping near the branches, junctions. When bubbles, drops, these kind of objects are moving, what kind of local turbulent futures they will really create. So there are bubbles which are rising in a column and they start shedding out hairpin kind of vortices structures. Based on their size, based on the Reynolds numbers and so on, different kind of characteristics happens. And that kind of things at fundamental level we try to understand. And something about swirling kind of flows. So there is some liquid jet which is coming and also spinning at entrance. So it starts spreading out and ligaments, filamentary kind of structures will be created. and specialized modes of instability is developed on this kind of spinning jets, and they start getting detached. Coriolis effects come into picture, and locally they detach. And something about boiling condensation kind of things. Bubbles are growing, condensing inside thermal environment. What will happen to them? And what kind of large scale structures do they create? In addition to that, we started looking at, you have channel flows, millions of particles are going superimposed, the high speed streaks, low speed streaks, which really pull these particles so that all these particles comes like structures, modify or modulate the turbulence. We are specially trying to look at, and that's the part of the story what we are going to see for today's lecture. The motivation, basically, if we are looking at extraterrestrial kind of environments, Mars, there are always be dusty storms. Instead of having clouds, thunderstorms, all these things happening on Earth like at some 10 kilometers, 20 kilometers kind of heights, these dusty storms usually creates thunders, electrostatic potential really creates lightning, all these things happens on those dusty streams. Similarly, landing kind of things in dusty environments, possibly racing kind of things. Maybe planes are moving on volcanic eruptions. So all these particles really get accumulated in gas turbine engines. Possibly moon landing kind of missions. Particles always be present in the system. Over that, if one is looking at typical chemical processing industries problems, there always be cold reflux classifiers, mineral separations at that point. You will have flow with particles interacting with each other. So the required achievement one will do in terms of processing capabilities. And even at oceanic kind of thing, recently sea missions like deep ocean missions are there, where plumes will be discharged into environment, where exactly they will go. These plumes, basically collectors will be there, they will collect these nodules, some kind of cleaning happens, the slurry flow goes all the way up, there again processing happens, the wastewater will be discharged. Now, the central question always comes like, how far these plumes really disperse and how long will they take? Whether they will have any impact near the seabeds and mid polar waters. That kind of things where this particle turbulence kind of things always comes. Usually, this kind of systems, in some sense, consists of particles, their clusters, maybe agglomeration kind of things. Compressible effects also present, turbulent, and they always be multi-scale in nature. You will see all the way to micron size to something like meter size kind of particles or perhaps solids. And they have big impact. Perhaps if you are looking at industrial pollutions, usually near these mountains hills, cloud formation is susceptible. And whatever this pollution by electrostatic kind of forces, turbulent motions, they go whether cloud to grow or not to grow, perhaps to condense, mainly depends on this particle or aerosol kind of mechanics. Similarly, any discharges in sea, recent floods in Kerala, the Delhi kind of environment, possibly the debris flow, the land erosion, all these things in some sense connected with slurries, particles, multi-phase environments. And all this initiated in SCRB called there was in 2017 via industry academic partnership. So along with Professor Abhinav from chemical engineering, and we have a joint student named Abhishek, we went visited Tata Steel. They have something named reflux classifier. Tata Steel always involve coal for burning, pulverization, and so on. They process this coal, separate them out. But then they will have these reflux classifiers. From one side, coal really comes, another side, liquid water comes, some kind of fluidization happens, and that pass through plates, separate them out. For that purpose, usually they see huge impact on these container walls. This walls water impact, suddenly there will be increase in pressure gradients happens in the system and mechanical vibrations, people start sensing it. Now the question really comes, which parts are prone for that? What is the mass loading acting on them? how we can really understand what kind of turbulence dynamics finally leading to structural vibrations. And usually they work at 200 tons per hour kind of processing rates. And these will be 6 meters, 3 meters in height. And the simple schematic, basically they use FS with kind of reflux classifier. This is the brand name of that reflux classifier. Usually, what you have is some fluidized water comes, particles will be fed, and these particles start sedimenting, fluid really goes, mixing happens in certain zone. Again, it passes through series of plates. And their place, these particles get attracted because of Saffman lift forces, they start sedimenting and more complex kind of environment happens. And that, what we want to understand, can we understand this entire turbulent mechanics here and also what kind of these sudden bends will be there. So your turbulent flow when passed through bends, immediately either Albers pressure gradients created, laminar separation bubble separated out, sometimes relaminarization kind of events also happens. So we want to understand this entire mechanics in simple toy model way. So that we try to model via particle-laden turbulent channels with additional information on them. So how to probe such kind of industrial problems? Basically, we can pretend this pole as a scalar acting on turbulence one way. The natural question comes whether it is a homogeneous isotropic turbulence on the scalar field I am going to understand, or should I really consider it like a wall-bounded turbulence. Similarly, I can pretend maybe these are spherical particles in turbulence, homogeneous isotropic turbulence on which particles are suspended, or maybe wall-bounded turbulence on which particles are suspended. Maybe pretend coal as crazy shape, size coming from industry standards or base measurements, but that's quite challenging environment. So something like collisions, breakup, agglomeration, electrostatics, and so on. Industry guys always wants that kind of complex problem. That's beyond present days computational power to handle. The easiest thing, what one can go ahead, do this high scale, high fidelity simulation turbulence along with particles is second one like pretending coal as spherical particles. Maybe one can really go with wall bounded turbulence with point particle kind of approximation. One can go fully resolved, but these numbers will be limited like hundreds, couple of hundreds, 100. When you are going for point particles, effective forces acting, instead of resolving complete full stresses on that, up to 10 million, 15 million kind of particles one can go. So we employ that second approach. The issues with this event, pretending like homogeneous isotropic turbulence with scalar is, there always be large scales, small scales really coming to picture. Scale separation happens when particles are suspended on that, they start showing intermittent corrections on that entire system. So simple phenomenological models like phenomenological theories may not work on this particle-laden kind of turbulence. And singularities always be developed on these velocity fields at these small scales information. And that is the place these point particles comes acting or perhaps particle comes apply forces on the system. So the locally they accelerate to infinite extent. So it's not that possible to simulate it with full resolutions on those scales. And also there always be clusters formed via ramp with kind of structures. The other way to pretend is let us do wall bounded turbulence, means there will be a channel, flow comes in this direction, maybe bulk Reynolds number something like 13,000, 14,000, 20,000, this kind of thing. There always be high speed streets, low speed streets will be there, and particles might be moving on them. So, based on how much volume fraction of particles one will be using, and whether these particles having inertia, do they immediately adjust with the flow? So there is some turbulent fluctuation, but your particle having a tiny inertia, so immediately it will be struck by this flow fluctuation. Or do they possess huge inertia, flow pushes them, but this particle resists the flow, modulate the turbulent fluctuation locally, but after a while it starts moving because of inertia. So it's really crazy kind of way these particles modulate the turbulence of the system. And usually based on the volume fractions, people try to look at whether particles can influence the flow. Particles can influence the flow, but it is more like two-way coupled. Maybe particles rotate and also influence the flow by creating rotary kind of structures, four-way kind of coupling. This is the way standard point particle approach what people do. Otherwise, particle like solid sphere one has to do resolve that entire thing by immerse boundary method kind of things, or perhaps write complete structural information, resolve these stresses acting on the particle, how these fluctuations really interact. That's another way to do. A typical industrial problem, the most preferable choice is whether it is gas turbine base on which your particles are moving, or perhaps industrial reactors where particles are moving. Basically, going with Lagrangian identities, but writing all your forces like inertia, buoyancy, possibly the drag acting on that, lift forces acting on that, and integrate with your fluid solver, try to solve it. But those studies also have their own kind of fallacies. At certain locations or certain problems, people reported the drag tremendously reduced by having these particles. Some studies says that drag tremendously increased in this kind of system. So there always be these arguments in which cases drag enormously increases, so choking or perhaps increase in pressure gradients develop, or where exactly drag really reduces. Usually, these particles behave in a very crazy way. Whenever there is a swirling kind of motion, if they have inertia, they will be thrown out by centrifugal forces. Wherever the vortex, basically, if we are saying integral scale of the vortex structure is there, up to that level, particles will be expelled. So you will have something like clustering kind of phenomena happens in these turbulent structures. And there are always be strain zones where they will be really pulled away. Based on volume fractions, they change topological nature of particles in turbulence. That means your ensemble averages or macroscopic nature of this entire drag completely changes. And that is the place, first of all, we need some idea about how this wall-bounded turbulent flows first of all works, because we want to understand flow through channels, turbulent structures on which particles are present. So the typical wall-bounded turbulent flows means there is a wall, flow comes from one location. If it is already the turbulent flow, possibly some viscous layers, some logarithmic layers, some mean flow always be there. And flow comes, and what we are seeing is the energetics, the kinetic energy in the flow. There are always be small size kind of eddies, structures, large scale, maybe if possible some kind of self-similar nature happens up to certain kind of scales. And the scales also may be small but highly energetic, may be large, not that energetic. That kind of interaction also happens. They always be multi-scale in nature. And if we are looking, the small scales very focused near to the walls where viscous effects are important. So any scaling based on viscous kind of thing one will be doing. Or maybe beyond that kind of thing, a kind of self-similar nature of these eddies happens, and those structures in some sense one can scale it via boundary layer mechanics. People try to understand this kind of wall-bounded turbulence, maybe on plates, channels, pipes, and so on. Usually, what happens is in this kind of wall-bounded domain, in between the small to large kind of scales, a kind of similarity happens. Your entire stress remains constant. This is the hypothesis. So that when that hypothesis happens, whatever the wall gradient near here will be equivalent of what gradients whatever develop because of turbulent structures from the mean, and also something like turbulent fluctuations whatever happen. So this remains constant so that one can construct scale-wise kind of arguments. And the scales also having something like instability mechanism develops, something like either hairpins or puffs kind of structures happens if it is complete channel kind of thing. Puffs comes, goes out and so on. If it is just pure plain walls kind of thing, hairpin kind of thing comes, bursts and create turbulence in the system. Based on that, you will have always very complicated multi-scale nature in terms of boundary layer things. That is the zones where some parts will move very fast and the rest of the parts goes very slow compared to the mean flow. So you always have something like shear kind of things, rotating kind of structures, elongating, high speed, low speed kind of streaks one will be seeing. And these particles really get suspended and modified, break these structures. And what people knew is from past 100 years, there always be command like logarithmic regions, so that in terms of wall coordinates normal to that wall, how velocity profile varies in terms of that normal coordinates. And people realize that up to certain accuracy, there is a chance that one will be going to see some kind of scale invariant kind of arguments. One can really look at in terms of command positions and so on. Channel flow is a bit more complex in terms of spatio-temporal features. And people realize that all these pipe, channels, wall boundary layers in some sense brought into one particular kind of framework if we can understand this structural component, what we are talking the structural like large, small kind of scales. Typically, the Xavier-Siemens results based on wall shear, usually channel flows and so on, how much shear happening. So shear stress I know, so that I can define something like Reynolds number in terms of shear stress. And that's what we call RE tau, based on the shear stress. When you increase that wall shear stresses or wall Reynolds number, these coherent structures, the red high speed, the blue low speed kind of structures, broken down into many tiny pieces, and if you are going, it starts showing multi-scale nature. The predominant high-speed, low-speed streaks always be there, but they always have multi-scale kind of fans coming out of these things.
What are these axes?
These are stream-wise velocity components superimposed on them. So the way in these turbulent boundary layers, there always be mean flow. If I am looking in these logarithmic kind of regions, are there any zones of flow which goes much faster than mean flow at the local level? Are there any layers which are going a bit smaller in velocity compared to the mean flow at the local level? So they create some kind of twisting kind of motions there, creating more stresses in the system. So understanding the structures always help us to understand how this drag really acts on the system. However, simulating such kind of 180, 950, 4000 kind of tau-based Reynolds number, wall friction-based Reynolds number, require grid points like RE tau 9 power 4. That means if it is 1000 cube, or even if I am taking 10,000 kind of thing, 4 gone, something like 1 billion points required to simulate this kind of turbulent wall statistics. And typically, the experiments always goes to 10 power 5 kind of wall friction Reynolds number. That requires something like 10 power 21 flops of information, 20 petabytes of data per time step one will be saving or handling. And a typical turbulent channel simulation requires 10 power 7 time steps to get accurate statistics in some sense.
What is meant by singular structures? Obviously, that is singular here.
So they always show some intermittency in the system. And that's the one which usually people connected with singular structures.
Is it
You are
spatial singularity? Is it some kind of?
you can say these are spatio-temporal kind of structures which are at very small scale acting, not like this kind of high-speed streak or low-speed streaks.
But I mean, it's singular in what? Is it singular
In velocity gradients. You will have huge velocity gradients. That means you will have huge turbulence stresses also created. So in some sense, this can be understood like low-dimensional models like high-speed streak, low-speed streaks. That kind of low-dimensional way of separating gives you certain kind of information on track. But these tiniest kind of structures are having huge velocity gradients. The size is small, but velocity gradients will be so large. So your stresses, turbulence stresses will be so high at that location. So now the integral of the volume to the stresses, whether that is very large compared to these large scale structures or small scale structures.
It's not singular in a mathematical sense. It's like moment as.
It's in an abstract way of similar because the velocity gradients are so large compared to the velocity gradients at other locations. And usually they show multifractal image. You can't even it's more complicated than multifractal. At least you will have some scale invariance goes in that. And typically, a channel flow of that range requires something like 100 petaFLOP of motion. And that's the challenge we want to compromise. We can't really go with that high Reynolds number kind of things, what industry wants, but at the same time, we can't compromise on the size part of this turbulence. So went ahead, looked at Reynolds numbers, wall, friction-based Reynolds number 180 to 400. Depends on what kind of configuration you want. So the simulations what we carried out something like 120, 180 and so on, all the way to 400 with different levels. And particles, now these particles are Lagrangian kind of particles, what we are trying to look at. So how quickly they will be pushed away by the flow to what kind of flow? So we are trying to construct the time scales involved in the problem. Do they carry huge inertia so that even flow fluctuation comes? They will not be in a position to quickly respond to that, or will they be immediately seen by that flow? That we characterize via something called Stokes number. If the Stokes number is very small, they will be immediately pushed swept by this flow. But if Stokes number is quite high, they start modulating the turbulence. And typically, we use 10 power 7 kind of particles, 10 million particles on 128 to 256 force kind of things. And the channel flow geometries will be something like 4 pi in length, 2 pi, 2 kind of units. Meshes ranging from 300 square kind of thing based on that. And typically, in terms of wall units, usually we talk about these simulations. This plus units, unless one or less than that, we don't really get accurate results. The mesh resolutions, instead of talking in terms of channel height, the wall units we will talk anything less than 1 and so on is good for these turbulence simulations. Go ahead, solve Navier-Stokes equation with additional forces coming from particles, and particles are Lagrangianly integrated with tiny inertia coming from them.
The common node that you were using to define Stokes, is that based on the wall shear stress or is it based on something?
I'm sorry, this P is no way connected with wall shear stress.
No, I'm asking about tau node.
Tau node is the wall shear stress, unlike this.
Okay, so it has nothing to do with the settling times.
No. So you have something like a mean flow going with 1 meter per second, but the turbulent fluctuations are coming here something like 5 centimeter per second, 1 centimeter per second, and so on. So any particle with 1 centimeter per second kind of thing, whether how quickly it really responds.
And how large, what's the value of the density ratio?
These are compared to water, it is 4 times, 6 times kind of density they will have, and also because these are mineral kind of things, what we want. Heavy dense kind of minerals, and also coal more or less equivalent of water. Something like 1540, 1560.
What is the
F is the drag force acting on this. Correct.
So it would be the same as the slip, right? That's what you're saying.
This translated there as a force acting.
And you are not accounting for the finite Reynolds correction to the drag.
Right now we are not doing, but that we have.
Consider gravity.
At this point, yes. These are highly turbulent things. Gravity is not main role, but the fluctuations, how those things happen, that is important. No, it's quite easy. But the forces, the magnitude of forces, what it really comes is, because this is for unit volume, so rho multiplied by g. So So 1000 multiplied by G is something like 10 power 4 kind of local forces acting at that location every point. But the forces because of these turbulent fluctuations are at least 1 order of magnitude more than this gravity. And can be included but for this. So now coming back to this results. So a turbulent channel with RE tau, right now we are showing something like 180 kind of RE tau. Particles are suspended, some 10 power 7 particles. So enters conditions itself is turbulent, it's not developing kind of. You already have a synthetic turbulence force and turbulence really goes out of the system. So what we are looking at is, this is wall normal coordinates. So this is the box, flow comes, flow leaves, particles are continuously spread from inlet and they are going up and down kind of things like the animation whatever I have shown, again I will play it. And normal to that wall, what we are trying to look at. And typically this unit 200 means almost we reach center of the channel. So from all the way down to center of the channel, this is the way we have to do. These are not periodic but outflow kind of condition. Whatever the structures comes, let them go. But synthetic turbulence every time enters. Whenever particles in symmetry, we will liquid particles. So the number of particles in the system always remains same. So because of some fluctuations, particles are coming out, mean flow coming out. Immediately count the particle, set it down. This zero is just zero. No. The local velocity of the flow with which it enters, that velocity with which particle. So we have a count on what is the particle which is leaving. What is this particle leaving? 2 particles left. Now choose random locations on this structure. At those 2 locations, whatever the velocity it is, because synthetic turbulence is coming in. So basically, it is 2 parts. One channel with particles going and so on. Another one without particles at all. So first we will simulate without particles the complete turbulent structures, whatever coming out with periodic kind of boundary conditions. For that unladen case, whatever the output really comes out, that will be fed as inlet to this system. Definitely. The momentum with which these particles leaving to the particles which are coming in is different. Inlet. Fixed kinetic energy in some sense ensemble average, time average on the structure. But it is not same throughout the channel range. Because here the fluctuation is different from here. I'm talking about inlet. It stabilizes the flow. It won't really increase the energy content in the system to a great extent. My understanding, maybe I have to interact with you more to understand your question. Otherwise, I will just open up my stupidity. So maybe after the talk, definitely I will learn it from this.
So you have the particles undergoing elastic collision.
At this level, no collisional issues.
So with the wall, what happens to the particle cross?
They immediately bounce back. Resource. Elastic
It's an
collision.
elastic collision.
But it's not really collisional mechanics, but immediately whenever it touches that wall, it comes up.
No, but what will be the moment post that time step? Will you reverse it by assuming it's elastic, or because you will be placing it so once it crosses the wall, you would basically say now it's back to its location above the wall. So do you also reverse the momentum assuming it's elastic process?
If you ask me in terms of momentum, it should be the same as kinematic kind of condition like in terms of velocity. Because
So for a scalar, you don't need to say anything. You just reverse the position.
Correct.
But because these are inertial particles, you need to say what is the velocity once it has crossed over the wall.
We don't do that. What we do is immediately the flip in terms of velocity. we apply.
So if it is flipped, that means the normal velocity is reverse. The tangential, nothing happens to it, so there will be an elastic collision, right?
You can say,
But you are not doing anything about the particle because. So I'm assuming this is very dilute.
this is very direct.
So there is
Less
no
than 1%
interparticle, nothing to bother about.
I'm not sure about that. But that's. I can't say that because it's dilute, I don't have to worry about.
But it is not there in the model,
But
right?
no,
There is nothing to do with particle-particle collision.
that can be activated, but we are not doing for the results whatever.
And in the wall also, when it approaches the wall, there is, at least even for the order 1 density ratio, you don't have aspects of lubrication coming.
No.
That's not there.
We don't resolve anything around the particles.
There's no.
They don't directly apply, but because if they locally apply a force via drag, that will be responsible
So
for it.
basically, a drag, I think, fraction of the particles. Drag.
You can say it in that way, but it's not necessary. Drag reduction happens even for the simple situations. Yes, sir.
Sir, I think you showed a slide where you had Stokes number versus constant. Where you had a column that showed one-way coupling, two-way, and four-way. So it's a combination of Stokes number as well as particle
Volume
concentration
fraction,
that decides whether we need four-way coupling or
or two-way coupling or one-way coupling.
so here
We have two-way coupling.
two-way. But it's low concentration, so
It's low concentration.
you don't need particle.
And also the diagram is now sacrosanct diagram. That is the way people work it out for a couple of problems. Whenever your geometry changes, the turbulent nature changes, there is nothing like sacrosanct about that picture. But that is taken it for granted, usually.
That was the 18th turbo.
So we always talk in terms of your particle time scale. In some sense, it comes via your setting velocities. The way how one will pretend is, you have one particle suspended in water, think about it that way. It reaches one steady sink kind of velocity. That means I will be in a position to really connect if particle is this, my gravity is so and so thing, in a viscous medium is so and so thing. I can really connect dp square, dp is particle square multiplied by whatever density by viscosity of the system, gives you a kind of time scale involved for that one particle. And the other time scale really comes via your fluctuations. But this time scale, again, is not a sacrosanct kind of time scale, but friction-based kind of time scale is what we are doing. When you are having large scale history, kind of thing, the time scales are different. When you have this kind of intermittent kind of things coming out and so on, the time scale is different. But this is wall friction-based average engagement.
So when you said that with the motivation that you have this whole slurry kind of a scenario. So you were saying the density ratio is almost equal to 1.
Different
For
for
gold, is that-
beneficiation.
Okay. So in that case, did you, consider how trustworthy?
Density we have usually.
No, I'm saying like in the model that you have, where you were just doing the linear Stokes drag, even if you add the weight term, that would not be an accurate description of
Correct.
real
We
density.
always have iron mass data.
So, everything else, all the other effects basically included. Is it possible to do it in this setup where you, I'm
Let
thinking
me
that,
reveal the secret. It can be done, but the main challenge for turbulent flow simulations is it's not about that complexity. The complexity comes whether we can really go with spectral way of accuracy in terms of even identifying the structures. These are something like second order kind of accuracy. This is completely useless for typical high speed streets, low speed kind of streets. So you will require something like spectral accuracy or at least some 6th order, 8th order kind of accuracy schemes even to talk. though I am there to present here, to talk even RE tau 400 kind of thing, you require spectral accuracy, on which you require particles. However, when you have particles on the kind of spectral accuracy, that increase because is spectral kind of thing. The errors in terms of identifying particle quotients is quite high compared to this kind of second order finite differences.
When you choose the particle size to be roughly half volumes, is that again coming from consideration of the?
Right now, there are many open sources available with fully resolved particles.
No, I'm just saying like what you have in your simulation. I saw that your particle size was around half volume. It's like 0.4 or something. Was that correct? TP was 0.4 volume. So, is there a reason why it is so large, or is that from?
But DP 0.4 not in terms of channel size.
No, volume units. 0.4 volume units.
Volume units. Correct, correct.
So I was thinking that when you have a particle that's that big.
No, that's actually small.
Because the weight of the particle would be.
Because one volume unit doesn't contain any structures. Usually, if I talk in terms of structures, your typical structures in logarithmic layers and so on, after 30, 40 volume units, they begin. So you have this entire viscous layers which are lying all the way from that 1 to 5 to 10 kind of sizes.
So is that 0.4? My question is that 0.4 coming guidance from the actual industrial problem, or is it because you can't? It's difficult to do very small strokes. Because I would imagine that if the particle size becomes very small with respect to volume, it's one place it is going to hit is that you have to do very small stroke simulation, which would be a very stiff kind of a system.
That is where fully resolved works. For Lagrangian particles, there's no problem in terms of part. In fact, it is more preferable to have small size particles in a box. Something like if I am taking my grid is this one. Think of this is one volume unit and so on, so kind of thing. Having point particle is more preferable rather than having this kind of
I mean, this entire simulation is point particle. What I'm saying is that having done point particle simulation, if you just keep increasing your Stokes number, that would make your simulation stiff.
That's true.
So is that the reason why you are having a particle size? So when the question is particle size being half volume units coming from the industrial consideration, or the fact that any smaller it would make computation harder?
That I need to think. But what I can really see is for typical Lagrangian particle kind of tracking and so on, the typical justification what one would require is, unless your particle size is way smaller than the smallest scale what you are resolving, you can't justify because any size comparable to that starts shedding weight, or perhaps you need to really resolve the stresses created around the particle. So the smallest turbulent structure is of that one unit, let us assume. Your particle is of two sizes. That means this national question comes, the philosophical question. I am pretending maybe 2, even though particle is way bigger. In that case, the turbulent structure, what you are saying is 1, but the size of the structure is way bigger than that. That means when that structure, the particle is moving, can't it generate additional high frequency kind of structures around it? And if that argument really comes into that, the entire Lagrangian method really fits. At least a point particle kind of thing. So because of that, usually they prefer a simulation point of view to justify the particle, whatever one is considering, at least supposed to be way smaller than your computational mesh. Any computational mesh of whatever they require. And second thing, you need to integrate it because it's not just one particle involved. Your velocity field to be integrated, resolved, distributed onto these points. But if your particle itself is of that size, how to do that is next question at Lagrangian point particle density. Maybe I need to talk a little bit more to understand maybe sensitivity or intensity of the question. Okay, fine. So we are looking in the wall normal direction, how this velocity profile, wall velocity profiles really changes. So what we are seeing here it is the continuous line is without particles, and that is the one within the 10 to 50 kind of units, possibly showing Karman's kind of statistics or log nature of that wall. Maybe from that 20 units to something like 50, 60 units, logarithmic boundary layers, one may be pretending. But having particles more on the system, immediately, whether it increases, decreases, leaving apart about that, immediately that log nature completely changes. And mean velocity profiles decreases. And that's based on one-way, two-way kind of things. How much concentration of particles within that box or perhaps in that particular slice of the system. We try to track it. Try to sense that. Possibly, if you are varying the Stokes numbers in the system, each layer may be having different kind of concentrations in the system. So your turbulent flow on which when particles are suspended, based on their heaviness and so on, the layers in those logarithmic boundary layers, the concentration distribution of particles also changes. Yes. Here, the Stokes numbers are based on wall units. That means at each layer level, we calculate what is the representative Stokes number. Because wall units, as we are going layer by layer kind of structures, your entire wall units are going to change. Your new components are going to change. Your local length states are going to change. In terms of the Stokes numbers we are talking about. It's not Stokes number throughout constant in this system. This is not the typical Stokes number dp square by 18 u by whatever average fluctuation what we are looking at. The time scale of the industry is very high. Much larger than the time scale of the fluid which is in daily. I may have to. I will get back to you. Then lastly, we calculated what is the skin friction coefficient in the system, the overall frictional coefficient, and particle densities are changing. What will happen to the system? Possibly Stokes numbers at this wall kind of units. Very high kind of thing typically behave like one-way kind of couple kind of systems. But if that decreases, naturally skin friction coefficient increases in the system, that also changes. The first result, the entire skin friction on the systems are dragged in some sense representation that entirely changes based on this particle mix. Similarly, try to calculate what kind of velocity fluctuations it will be seen, RMS kind of quantities in the wall normal kind of coordinates. Near logarithmic kind of layers, modulation of the turbulence really happens. So this entire RMS fluctuations gradually changes in the system. So what we are seeing continuous line is typical wall bounded turbulence. But if we are putting particles more into the system in very non-monotonous way, it will be modulated. The Reynolds stresses also changes in the system. So the Reynolds stresses effectively decreases in the system, but your mean kind of gradients at certain layers increases in the system. And then calculated how these production terms, kinetic energy, transport terms, and so on, different terms in the system behaves when these particles are suspended in turbulent environment in the wall normal coordinates. So when we are going with wall normal coordinates, the typical energy budget shows that. So right now what we are seeing is jet. So this is complete balance of the terms pi b. So something like the Reynolds stresses, what kind of fluctuations energy extraction happen, the production term, what is happening in the system, to particle driven kind of source of energy, to how much really dissipated out. That entire summation, what we are showing as a function of wall number properties. So usually at logarithmic layers, this entire term, basically the transport term comes because of this production, the forcing term with the dissipation kind of term, usually high logarithmic layers, that is the layers where you have this high speed, low speed kind of strings develops, start moving. And those really get start modulated by these particles. And that's the thing what we started with. And then went ahead, try to include even pressure terms in the system, how the entire pressure fluctuations really changes on these entire structures, and particles have big influence on those structures. Basically, the overall result, what is happening is, when you have particles in the system, logarithmic layers are disrupted, but the viscous sublayers start modulated and we start creating more and more turbulence in the system. So usually your logarithmic layers are the ones responsible for production of the terms via your streaks, ejections, all these mechanisms. But that becomes a bit calmed down. But below that, these particles start agitating the flow and start creating huge modulation of turbulence. So your viscous sublayers actually becomes agitated in the system. And the overall summary is, in turbulent channels, when particles are present, the typical Karman law kind of things first up, whether that is applicable to or not, leaving apart about that first of all get changes. Usually they go towards the walls and start disturbing this entire system below these logarithmic layers. And wall friction increases in the system, and that augments viscous sublayers but decreases logarithmic layers. And this entire work went for this. That's all about this talk, and thank you very much. Thank you, Mani and Anubhav, Amin and Krishna. Thank you, ma'am.
Any questions? What is the width of the equation?
Are you referring to any particular size? Are you asking about the channel width? Oh, in general. Okay. But these are wall mounted turbulence, so I'm not sure. I'm not sure that I'm supposed to show any K or minus of there. Because it's a wall mounted turbulence. Whether it increased or not. I think yes, but I'm not in a position to answer you very deeply. Because most of the energy production happens in this logarithmic figures, that means depleted. That means the range supposed to be narrowed down. That's my first answer. Now, the viscous sublayers which are not turbulent, but that range is not increasing. Because that's the one where most of this turbulence is happening. So I'm not sure whether I can answer your question in that way, but I need to check this. I have it. These are fine here. Viscous sublayers of unlighted particles. Any questions?
what is the subset?
Sorry. Let us go with students.
Yeah, like
Hi, please.
If the particles collide, so in that time, what happens is the moment of collide elastic or inelastic,
In general, one requires that. Even to collide, there always be lubrication layer when they are necessary. Whether they will really rupture those lubrication layers comes from small, I'm not sure. But this model doesn't go with any particle. Usually, the particle positions are so important in the case of dry granular kind of media, granular forms, wherever positions are more important. But when these particles are suspended, as suspension kind of thing, the most important thing in my understanding, and I will wrong also, they come closer and closer, the liquid investigate really get ejected out here. They become so small. Now the extent gets affected, the lubrication pressures becomes, it becomes more small, disjoint pressures and contactile mechanics and more complex kind of stuff. So I'm not sure how it really works. But this model doesn't have those things. That comes from basically the drag force and impact force. And what are the external forces that you can make? Yes.
how do you define it? So for the definition of what is asking. So when you have this point, then is it put down or is it exactly the so your particle is not necessarily smaller than your zero, or larger than it.
My particle is always smaller than because I'm not reserving any particle. There is some point on which some effective forces acting on the system. Maybe it's extracting the so on. So no stress information, it's only force.
So this force is it put down over the physics or is it how do you allocate it?
That's the challenge really comes. So usually cubic interpolations we require. So you have 2-3 particles acting on the local velocity information has to be distributed. How close it is. So if it is something like a line, you use a cubical kind of square that in 2 coordinates is supposed to know. 3 coordinates like 3-dimensional kind of. Then cubic kind of thing comes via x, y, z kind of. It has to be applied with it. That always have is interpolational errors involved in the system.
And all the simulations are made.
Yes.
So, I mean, what is the difference between this that you look at? Is it only the type of turbulence that you have, or is there any other thing?
And now so that's more difficult question for me to answer. What is the importance of 2D? When you are shrinking the dimension, what happens? I'm not sure. First of all, the typical turbulent structures you may not see. More of chaotic in nature, chaotic diversion, you will start sensing. What are the extra things happens because of that? I'm not sure. You will always have these kind of rotating kind of structures where particles will cluster, they start coming agglomerating and so on, so kind of thing. So the physics to incorporate there will be more trickier than 3D environment where the same volume fraction one is using. Because these particles, they may not accumulate together, they start dispersing here and there. But when you are shrinking the entire third dimension for the same volume fraction, they have to be fit locally to that. That means particles may start coming more closer and closer to each other. And naturally, the additional physics comes along. More important in some sense. Correct.
And one so You were saying that we have lost the boundary theoretically the value.
This one, repeat like that side or this side. Aha, okay, got it.
Yes, yes. The constant stress. I know that. Your weight will go
You should attend Congress was given by science. You can't just hang around and apply against all of it. If you come and visit Europe, have complex challenges like uh, boundary layer theory, turbulent boundaries. As it was then the conclusion was that that was supposed to be good. But two of particles maybe form certain kind of cluster. It's not that's not the real of this. As a collective unit, they may be that would be interesting, right? You may trying to understand what kind of spatial organization is happening in these communities.
Oh, that is good.
So these are mainstream kind of components. Mean, not the streamwise velocity uh, color coded on this. There's no white. White means you just scoop out that information. Local flow velocity, color code.
any other questions that this is over me? Okay, last question. There is one last question.
Please, please. Definitely. But I don't know much about that spatial development. The point is, even body parts are necessarily size. That's the question what I was trying to ask. The bigger question is it's not about whether particles bounce on the wall or not and so on. Even what it means particle, usually any industrial problem always have crazy shapes. This spherical kind of thing is very abstract. They will be very sharp kind of things. They will start interacting with each other. More complex kind of shapes you will have. They are not spheres, they might be cylinders, tapered, very, I mean, like just take sand grains and try to sense them. That kind of shapes they will have. Now, if I want to simulate that, how am I going to do? Discrete and kind of simulations are the only way. But when you are using that, how are you going to really resolve it? You require billions of particles moving around us. How to do that? So, Right now, what we are trying to talk about, whether particles come together, collide, what kind of lubrication, that means already we are trivializing the problem to really look at local level how these particles have to interact. But the much bigger picture is for any university kind of problem, these particles are variety of places here. It's not one universal here. They will have distributions. Something like few micrometers goes to few millimeters to few centimeters kind of distributions. Whatever this is, I say, this system is multi-scale in nature. That kind of, they come in back, break into parts, that kind of small kind of things are going. They come together when the gravity kind of things are happening, electrostatic forces will be generated, they start attracting each other. So it's more complex problem. In some sense, what I have shown is very trivialized kind of problem. Okay. And, another one more. Thank you very much, guys. It's my pleasure to visit you and learn from you.